Now, since we have finished with Ohm's law, we have seen ohmic devices, non-ohmic devices. Let's move ahead and look at resistivity. Now, the understanding of resistivity that we have is from the expression of resistance. R is equal to rho times L by A, or rho is equal to RA by L. Now, here we have three categories: conductors, semiconductors, insulators, and their resistivity is given. There is temperature coefficient of resistivity. We will not look at that right now. So if you look at conductors, semiconductors and insulators, you can see that the power that is there, we can ignore the number and look at the magnitude. So 10 power minus 8 is constant for all conductors, whereas for semiconductors it starts at 10 power minus 5 and then there is not much. Silicon has 23 into 10 power 2, and if you look at insulators it reaches up to 10 power 16. So this is a huge range of resistivity from conductors to insulators. Now, what is the understanding that is there? Another factor that we had seen when we saw resistance was it depends on the nature of the material that is there. So here, if you look at conductors, the resistance is supposed to be high or it has to be low. It has to be high in the sense we need certain amount of resistance to be offered for the flow of electron. But if you look at it from a macroscopic view, that resistance is going to be very, very less. But for that electron to pass, it would have felt a huge amount of resistance. Now, since resistivity is in 10 power minus 8, the resistance of all these elements that are given, or let's say these metals or these conductors that are given, is going to be very, very low. So if you see silver, as I had previously told, gold, silver and copper, these are the three best conductors of electricity and heat. So that means there is going to be minimum resistance that is offered. But if you look at aluminium, tungsten, iron, again there is some amount of resistance that is offered which is more than pure gold, silver and copper. We also have alloys, which is, let's say, nichrome, which is an alloy of nickel, iron and chromium. Manganese, again another alloy that is used in making resistance boxes. Let's go to the other end of the spectrum. We've got insulators. Now, insulators are these type of conductors or materials which offer very high resistance. Now, the usage of the word conductor is not correct because these are just materials. They do not conduct anything. So if you look at pure water, glass, hard rubber, sodium chloride, fused quartz, these are insulators. Mind you, regular water that is there, you will actually feel the shock. It is a conductor. But pure water, what happens? We remove all the dissolved components that are there. Hence, pure water does not act like a conductor. It is an insulator. Now, another category of these elements come in between that of conductors and insulators, which we call as semiconductors or semiconductors. So they behave both as conductor and as insulator depending on the time and temperature. That means at low temperature, they can behave as conductors, and as temperature increases, they can behave like insulators or vice versa. Now, that depends on the amount of current that is flowing and the functionality of these semiconductors that are there. We will discuss this in detail in a later chapter. Resistors. Now, this is the most important part that is there in any electrical circuit, because based on this, the circuit can either survive or it can be destroyed. So if it is a high resistance, we might not have excess current that is flowing. The circuit can be safe. If it is a low resistance and allows the entire current to pass, the circuit can burn. Again, that depends on the type of circuit and the type of resistance we are talking about. In the commercially available resistors, we generally have two important types. The first one is a wire-bound resistor, and this is made by winding wires of an alloy, that is manganese. Now, this is something that all of you would have seen in your labs. This is a resistance box. So inside this resistance box, you can see that there are multiple windings that are there which are connected to one of these pins. So if you're going to plug out, if you remove, let's say, this plug or this pin out, that means that much amount of resistance through this wire you've opened. You've opened the passage of current. If all the pins are in place, there is no current going to flow. So this is a resistor. But if you remove one of the pins, depending on the value of resistance that is given, that much amount of current only will be allowed to flow. These resistance boxes are huge, quite bulky. We can have resistance up to infinity. So this last knob that you see here is an infinity resistance knob that is there. That means it gives you infinite resistance. Now that, let's say, if you are going to tell we just have a length of wire, how is it going to happen? We use certain principles and procedures that are there in order to arrive at an infinite value or a huge value of resistance that is there. Now this is the first type. The second type, which is a favorite for all, is something called as the carbon resistor. If, let's say, we try and compare, the resistance box can be a 15 by 5 centimeter box. So 15 cross 5. So it is going to be 75 centimeter square area. But if you look at this carbon resistor, its area is going to be sometimes 1 millimeter or even less than that, 1 millimeter square. So it is very, very small device, and this can be implanted. If you have a look at your computer chips that are there, these are implanted in those chips. In any electronic device, resistors are there, and these are color coded. Now, since it is a carbon resistor, we can't tell the number of windings that are there and talk about length and then try and figure out what is the resistance. The only way that we can do this is by using the color coding that is given. Now, if you look at the color coding, the first one, band A is the first digit, band B second digit, band C is the multiplier, and band D is the tolerance. So let us look at what this band A, B, C, D is all about. So here is the color combination B, B, R, O, Y, G, B, V, G, W. Okay, fine, doesn't make much sense. But if you look at the diagram that I have given here correspondingly, you can see that the first one, black is 0, brown is equal to 1, red is equal to 2, orange is 3, yellow 4, green 5, blue 6, violet 7, gray 8, W white. Now, question is how to remember this combination. So there is an anagram that is passed down from, let's say, student to student or teacher to student in order to understand or remember this. So the anagram is B.B. Roy of Great Britain had a very good wife. The only thing that you have to understand is B and B, black and brown, you should differentiate because the sixth one is going to be blue. So first digit, second digit, multiply, tolerance. So what is the meaning of this? So let's have a look and write for this present combination. So it is blue. The second one is what? Number 2, right? So it is red. Then you have got a multiplier that they've given it as black. And then they've given the tolerance. So blue is number 6. Red is number 2. Multiplier. So this is into 10 power 1. Or since it is black, we will not take 10 power 1. We can just simply take it as 1. And plus minus 5%. Now the tolerance, it depends on whatever color is given. So it's yellow, it's generally plus minus 5%. 1 and 2% is sometimes there, not always. Let us see something like this. If I give you a combination of green, so I'll just write it as green, blue and yellow. Now let us see what will be the resistance that is there. So for this, what we will do is we'll go to the next page. So I've given you green, blue and yellow. So the first one is green. What is the number that is there? Green is 5. Blue, what is the number? Blue is 6. Yellow, what is the number? 4. Now how do we write this? So first digit, second digit into 10 power the third digit that is there. So apart from black, any other color that we get, we are going to have into 10 how much it is. So there's going to be 10 ohms, brown is 10, black is 1 ohm, brown 10, red 100, orange is 1 kilo, yellow 10 kilo, green 100 kilo, blue 1 mega. So this is going to be the resistance of this present given combination that is. Now this color coding pattern that is there, it helps in identifying any resistance that we need. So we can figure out what type of resistance we need in a circuit for the amount of potential difference and the current that we are supplying. And along with that, how much resistance we need in the circuit if we can calculate. Correspondingly, either using one resistance or, let's say as I've shown here, multiple resistances we can connect to get that particular amount of resistance and then make sure that the circuit works fine. So now, since we have done with different types of resistors, we have seen ohmic and non-ohmic devices, we can go ahead and look at how the temperature dependence of resistivity takes place. So right now we had seen temperature dependence of resistance, but resistivity we hadn't seen. So for resistivity, we can actually go back uh, to a little bit of basics. That is, in our understanding, resistance is given as rho times L by A, or I can write it as rho is equal to R times A by L. Now this is the most basic expression that we have. But if we go into, let's say, a little more detail of this, then we have to express it in terms of one phrase that we saw at the beginning. That is temperature coefficient of resistivity. Alpha was something that was shown there in that table of resistivity of the materials. So we can go ahead and try and figure out what that is. So for that, we will use the following expression that is there. That is rho t is equal to rho naught of 1 plus alpha of t minus t naught, where rho t is the resistivity at temperature T and rho naught is resistivity at temperature T naught. So we have a reference temperature and then we have another temperature where we can measure rho T. Alpha is the temperature coefficient of resistivity. Now we also have let's say resistivity in terms of conductivity. That is rho is equal to 1 by sigma. Now this can also be written as m by n e square tau. So you can see that the resistivity is inversely proportional to the number of electrons that are there. M and E is a constant. So if the collisions are going to be timed perfectly, then tau also we can estimate it to be a constant. So the variation of resistivity is inversely with that of the number of electrons that are there, which pass when a specific potential difference or voltage is applied. So let us go ahead and look at the resistivity versus temperature plots for a couple of different items here or different substances. Now the first graph here, as you all can guess, it is resistivity versus temperature, but this curve looks similar to V equals IR curve, the V by I plot. Now this curve is for a conductor. So we can see that for a conductor, resistivity keeps on increasing exponentially with the change in temperature. Whereas the second one, it's not an insulator, it is for an alloy like nichrome. This is how its resistivity increases. So with temperature, so up to, let's say, even when they begin at 0 Kelvin, it has a very high resistivity, and then as temperature increases, this resistivity continuously increases. In case of semiconductors, it is reverse. You can see that the resistivity that is there keeps on decreasing with temperature. So lower the temperature, higher the resistivity. Higher the temperature, lower the resistivity. So electrical energy and power. Now when we take this concept, the idea is to understand what is the power of a given circuit. When we tell in general power, we are able to easily relate it to the amount of energy that has to be possessed to do work. But in terms of electricity, when we talk about power, it becomes a little vague, because what is the meaning of power? So here we are going to see mathematically or using certain expressions, diagrams and derivations, what electrical power is and what electrical energy constitutes. So here I will start off by taking a cylindrical rod which is a metallic conductor. So these are the surfaces that are there. I've got two surfaces as I've shown here. So this will be the direction of charge, and again, if I connect this entire thing into a circuit, let's see what will be the direction of current. So let's have positive, negative. Okay, good. So this is our potential difference. Now we know that current always moves from positive to negative. So also will be the conduction of charge that is there. The electrons as such are moving in the opposite from negative to the positive. Now if I take two faces A and B, it is understood that the potential at A is greater than the potential at B. Therefore, our charges will always flow from A to B, higher potential to lower potential. So if I tell delta Q is the amount of charge that is flowing in a time, let's say delta T, and if I is the current, I have delta Q is equal to I delta T, because current was nothing but rate of flow of charge per unit area perpendicular to the flow of charges. So this is what we get, delta Q is equal to I delta T. Now let us look at the potential energy of the charges at A and B. So at VA, or I can take the potential at A. So potential energy at point A can be taken as VA times Q. Similarly, potential energy at B is equal to VB times Q. Now, the change in potential is something that we have to see. So the change in potential will be nothing but QB, or let's say we take it like this, Q of VB minus, because it is nothing but final energy minus initial energy. Final because at point B it terminates, at point A it is originating. So I can write delta U is equal to Q times VB minus VA, which is also equal to minus Q times VA minus VB, which is equal to IV delta T. Now this value is going to be less than 0 because it's a negative value that is already there. Now if I take delta K as the change in kinetic energy, then it is implied that delta K will be equal to minus, instead of U, we can take delta U since we are all taking small changes, delta U, and this will be equal to IV delta T, which is now going to be again less than 0. So there's a negative sign which comes because of delta U being negative. And that negative sign is lost when we substitute it here. So I get plus IV delta T, which is greater than 0. Why? Because negative was less than 0. The moment it becomes positive, it becomes greater than 0. Now, if we have to figure out how much is the work done. So if I take delta T as the amount of time in which work has to be done, then I can write delta W is equal to IV delta T. Now this is from work energy theorem. That is, work and energy are interconvertible or they are equivalent. The power that is there is given as work done per unit time, delta W by delta T. So if I substitute, I would have IV delta T whole divided by delta T. So I have got P is equal to VI, or I can write P equals IV. Both are equivalent. Now, from Ohm's law, I know that V is equal to IR, and I've got power is equal to IV. So if I substitute for V, I will get power as I into IR, which is equivalent to I square R. But if I substitute for I will be V by R. So power is going to be V by R times V, or the power is equal to V square by R. So depending on how you are framing your expression, you can have P is equal to I square R, or you can have P equals V square by R. It can be in the numerator. Resistance is in the numerator when you're looking at current. It is in the denominator when you're looking at potential difference. Now the question arises, from where does this power come? So this power that is there comes basically from the movement of charges. So if I take, let's say, a bulb, and if I connect it to a battery, the bulb is going to glow as soon as I have the battery that is connected. Now, in this case, movement of charges is there. But if I have to talk about power of this battery, what is happening here in a battery or a cell? Battery is a collection of multiple cells. We have the chemical energy that is there being converted to electrical energy. So chemical energy, we have electrolysis that is taking place, because of which the electrical energy, movement of charges, produces electrical energy, which gives rise to power in this particular circuit. So if we look at, let's say, transmission of power, so we would have the station from where the power is generated, then through wires it comes through these huge transmission cables that are there, then it would go to a grid substation. From there again it is given out through cables, poles are going to carry them, and then finally it reaches your house that is there. Now in all of these cases, it has to be kept in mind that the voltage that is there has to be very, very high. That is when the current that is there, or basically the potential difference, will be maintained such that we get a constant current in our houses. Otherwise, what would happen? At every point, there would be dissipation of energy. By the time we would receive current, it would be very, very low. So this is one more very good and important advantage of the expression P equals VI or P equals IV, transmission of power. So when we draw our electric circuit, we generally represent a resistor with this kind of a squiggly line that is there. Now it is seen that in a given circuit, let's say if we take a household circuit, we will have a television, a mixie that is there, let's say a washing machine. These are huge equipments which will be connected. On the other hand, you will have, let's say, bulbs, you will have tube lights, you will have fans that are connected. Now these are smaller, so that means the power consumed by these three will be very much small compared to these three. So we can have multiple resistance in a circuit, and how do we go ahead and write it is the question. So what we do for this is, let's say if we have one resistor, we generally write it as R1. Let's say two resistors, we write it as R1 and R2. It can be in this format or it can be in this particular format. Now again, it depends on how we want the circuit to function and what it should function as. So these are multiple ways in which we can represent given resistance. It can be one, two, or more resistance. Now, the way how I have always looked at looking at the current is it flows. So basic understanding is current flows. And now we're telling since current is flowing, it will be along a path that is given. So here in the first case, if I see, this will be the direction of flow of current. Through this resistance it goes, and it sure does come out. It might not have the same magnitude as it had earlier. Now when I look at it from the second one, the second diagram, this will be the current, passes through resistance R1, again comes out, passes through resistance R2, and again comes out. But if you look at the third one, it is like having a stone in the middle of a flowing river, so that what happens? The river splits apart. So when it splits apart, it is no longer one stream, but rather two different streams that are there, or not one river, but two rivers. So same thing happens here. I have current I, and that splits into I1 and I2. And finally, again, it meets up again here and comes out as I that is there. Now, with this idea in mind, we can go ahead and try and look at two important circuits with resistances. The first one, that is the one given here, is called as a series connection, and the second one is called as a parallel connection that is there. So first let us look at series connection. So in series connection, what we will do is we will draw a circuit so that we know what we are looking at, and then things become a little easy for us also to solve. So here is my circuit. I'll open up a small space for my cell, and let's say we'll place three resistors that are there in series. So I've got plus, minus. This is my first resistor. This is my second. This is my third. As usual, we will write this as R1, R2, R3. This is the direction of flow of current. This is the potential difference that is there. So now if you see in this circuit, current is starting from the positive, going throughout the circuit and coming back to the negative point that is there. Now, if I look at the potential as such, it is not the same for R1, R2 and R3, but rather it is divided. So I've got V1 here, V2 here, V3. That is because if I am trying to measure the potential difference across each of these three resistors, it is going to be different since the current that is flowing through them is going to be different. We are not going to have I1, I2, I3, but rather the current that is flowing through resistance R1, its magnitude would have decreased because of the resistance. Again, it goes through R2, it would have further decreased. Again, goes through R3, it would have further decreased again. So that is the idea why we label this as V1, V2 and V3. So we can go ahead and tell that the total potential difference that is there, V is equal to V1 plus V2 plus V3. And since V is equal to IR, what we can do is we can do the substitution, because if you see, V1 is nothing but IR1, V2 is equal to IR2, V3 is equal to IR3. So I go ahead and substitute in V is equal to V1 plus V2 plus V3. I have IR is equal to IR1 plus IR2 plus IR3, or IRS is equal to I of R1 plus R2 plus R3, or RS is equal to R1 plus R2 plus R3. So the resistance in series, when I see, it simply adds up. All the resistances just get added up. Now let us look at the parallel combination. So let's draw a circuit for a parallel combination. This is how my circuit is going to look. We will, like last time, we will take three resistances only. So I will just yep. So this is my first, second, third resistance. This is the EMF that is there, the potential difference. Same like last time, I'll take this as R1, R2, R3. This is my potential. Now if you see, the current that is there gets split. I gets broken into three, that is I1, I2, I3. Now the potential here would remain the same because if I'm trying to measure across the ends, R1, R2, R3 are all stacked one above the other. So V remains the same, whereas I keeps on changing. So in this case, I will have the total current I is equal to I1 plus I2 plus I3, and V is equal to IR, therefore I is equal to V by R. Now let us substitute. I will have V by R is equal to V by R1 plus V by R2 plus V by R3. So this I can write it as V by Rp, since it is parallel, as V by 1 by R1 plus 1 by R2 plus 1 by R3. The V will get cancelled and I will end up having 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Now this is the combination of resistors in parallel that is there. Let us say instead of 3 resistances, I had only 2 resistance. So 1 by Rp, I can write it as 1 by R1 plus 1 by R2, or 1 by Rp is equal to R1 plus R2 by R1 R2, or R parallel is equal to R1 R2 by R1 plus R2. Now this is a useful formula when we are looking at competitive exam questions that can be asked. Now since we know that the currents are different in the branches that are there, we can estimate branch current that is there. So for that what we will do is we will take two resistances and we'll try and find what is the branch current, and accordingly we can go ahead and solve for higher values that are there. So if I take this as my cell, I've put a key here. I've got resistance R1, R2. This is the current. It splits into I1 and I2. This has a certain potential that is there. Now, the total current is nothing but I1 plus I2. This is the total current that is there. But if I let's say take potential difference. If I look at potential difference, V across R1 is the same across R2. Potential difference across R1 and R2 are one and the same. So we can go ahead and we can write from Ohm's law, VR1 is equal to IR1, VR2 is equal to IR2, or since they are equal, I can have I times R1 is equal to I times R2. So from here, we had a small error, I think. Yes, it has to be I1 and I2. So I1 R1 is equal to I2 R2. Resistances need not be the same. Or I1 by I2 is R1 R2 by R1. Next, we will add 1 on either side. That is, I1 by I2 plus 1 is equal to R1 by R2 plus 1, which will yield. So I will get I1 plus I2 by I2 is equal to R2 plus R1 by R2. Now I1 plus I2 is nothing but the total current. So I is going to be equal to I2 times R2 by R1 plus R2, or I by I2 is equal to R2 plus R1 by R2, or I can have I2 is nothing but I R2 divided by R1 plus R2. Now we know that I is equal to I1 plus I2. We have just calculated I2. So I can go ahead and find out what is I1. I1 will be I minus I2. And substituting, it becomes I minus I times R2 divided by R1 plus R2, which is nothing but R1 plus R2 of I minus I R2 by R1 plus R2. So I1 becomes R1 times I plus R2 times I minus R2 times I by R1 plus R2, or I1 is equal to I R1 by R1 plus R2. I found out my second current. I2 is nothing but I times R2 by R1 plus R2. So these are the values of branch current. So if we add them up, let us see whether we get I. So I1 plus I2 is equal to I R1 by R1 plus R2 plus I R2 by R1 plus R2, which is equal to I. So now since we have seen the resistance in parallel, let's go ahead and find out what are the individual currents, because it is noticed that we've got two different currents. So for that we will take a simple circuit with two resistances such that they are parallel to each other. Now from this we will go ahead and find out what is I1 and I2 and see if we can arrive at a general relation how we have arrived for the resistance in series and parallel. So yes, I've connected everything. Let's go ahead and put in our resistances. Yes. So this is going to be my first resistance, R1. This is my second resistance, that is R2. I will have a cell here, positive, negative. So this will be the direction of flow of current. Here I am going to have the split. So I can take this as I2 since it is going through R2, I1 which is going through R1, and then I have it coming back. Here I have a plug key where I've inserted the plug for the conduction to take place. Now we know that I is nothing but I1 plus I2 since it is splitting here, and since R1 and R2 are parallel, that means since they are parallel, I can take that the potential difference is the same. This is something that we've just seen. So if this is V, the potential difference here in between R1 and R2, so this length will have the same potential difference V. R2 will also have the same potential difference V. Ohm's law is V is equal to I times R. So we can utilize that and write V1 is equal to I1 R1. Oh, sorry. Okay. And V2 is equal to I2 R2. Now, V1 is equal to V2 since we can give the reasoning that R1 parallel to R2. So that implies I1 R1 is equal to I2 R2, or I1 by I2 will be equal to R2 by R1. Now let us add to both the LHS and RHS. We'll add 1 there. So I can see I1 by I2 plus 1 is equal to R2 by R1 plus 1. Let's take the LCM. I1 plus I2 by I2 will be equal to R2 plus R1 by R1. I1 plus I2, we know it as I. So I divided by I2 is equal to R2 plus R1 by R1. Or I can go ahead and find I2 will be equal to IR1 by R1 plus R2. So this is I2. Now since I have I is equal to I1 plus I2, I1 I can take it as I minus I2. So that is nothing but I1 is equal to I minus I2 was I R1 by R1 plus R2. I times R1 by R1 plus R2. We'll take the LCM. R1 plus R2 of I minus I R1 by R1 plus R2. That is I times R1 plus I times R2 minus I times R1 by R1 plus R2. So I can see that IR1 minus IR1 gets cancelled, and I will have I1 as nothing but IR2 by R1 plus R2. I have got I2 is nothing but IR1 by R1 plus R2. So if I'm taking branch 1, that is the top branch in our diagram, if I'm taking the top branch, this is going to be R1. The bottom branch was R2. So current I1 will be nothing but total current times R2 divided by the sum of the resistances, or current I2, that is in the second branch, is nothing but I times R1 divided by R1 plus R2. So now if I simply add I1 plus I2, I will get it as I times R2 plus I times R1 by R1 plus R2, which comes back to this expression, that is I is equal to I1 plus I2. So we have arrived at the expression which we started, that is I is equal to I1 plus I2. If we see here, we started with this. So we have found what is the individual current. We found what is the resistance in parallel for this combination. And we also know now what is going to be the individual currents in those two branches, since it is a parallel circuit, that is. Now let us go forward and see what is the difference between these two combinations. One is series combination, the other is parallel combination. So as the name suggests, the connection is in series. Whereas here connection is in parallel. Let's look at the second difference. Here if I'm going to take a combination of resistances, that is our, let's say, series combination, it is going to be just a normal addition of all resistances. That means if I take n resistances, I have written it using the summation, where Ri, subscript I means I can substitute 1, 2, 3. It is something like this. R1 plus R2 plus etc. up till Rn, we sum it up. So this is the general expression that we use for series combination. We don't use this entire formula. Similarly, if I take for Rp, this I can write it as summation 1 by Ri, I varying from 1 to n. That means I am looking at 1 by R1 plus 1 by R2 plus etc. plus 1 by Rn. Let us look at the next difference that is there. The important difference that is there is the potential difference that is there gets divided. Whereas in parallel, current gets divided. So let us put the expressions for potential difference and current and see what we. So if I see here, when I tell potential difference is getting divided, I will have it like this. V1 is to V2 is to V3 is proportional to R1 is to R2 is to R3, because current is the same in a series combination. Whereas in parallel, I have got three different currents. I1 is to I2 is to I3 will be equal to 1 by R1 is to 1 by R2 is to 1 by R3. So what have I done? Parallel combination, voltage or the potential difference remains the same, the current varies. The next major difference that is there is in terms of the equivalent width that is there, or in this case we call it as the equivalent resistance. Now when we plot a graph, we do get a couple of terminologies which sometimes is used in the theory, but let us stick with what you know. So Rs is the effective resistance in series, or the total resistance in series that is there. So if you look at Rs, we have seen it to be nothing but R1 plus R2 plus R3 etc. up till Rn. That means the total resistance that is there in series is going to be greater than the individual resistance, or Rs will be greater than the Rs greatest resistance that is there, or the largest resistance that is there. For instance, if I have 1 ohm, 2 ohm, 3 ohm, 3 ohm is the largest, but if I add them up in series, I'm going to get 6 ohms, which is larger or greater than the greatest resistance that is there. In a similar way, we can look at what happens in the parallel combination. Now, parallel combination, we have seen that 1 by Rp is nothing but 1 by R1 plus 1 by R2 plus 1 by R3. So from this we can understand that the Rp that is there will be lesser than the R least that is there. We'll just write it as R least, not 1 by. The reason I'll explain. Now, in this case, if we take R1, R2, R3, the least resistance, so this is 1 by 1 plus 1 by 2 plus 1 by 3. So this is just going to give me 1 plus 0.5 plus 1 by 3 will be 0.3. If I take, add them up, so it is going to be 1 plus 0.5 plus 0.3, 0.3, we will get 1.8. Now what is Rp? 1 divided by 1.8. So we are going to get a very, very small value. That is what this statement means. Another difference that is there is this. Now this is very important, that if I have n similar resistances, then for series combination Rs, I can simply write it as n times R. And in parallel combination, if I have n similar resistances, then Rp is going to be nothing but R by n. Now when we tell n similar, let's say we have 10 resistances in the circuit, all having let's say the resistance. So each R is given as 1 ohm. So if I have n is equal to 10 resistances with the resistance equal to 1 ohm, then Rs is just going to be equal to 10 ohm. On the other hand, if I look at Rp here, we'll take the same example. N is equal to 10, each resistance is 1 ohm. So if I use it here, Rp is going to be 1 by 10, which is going to be 0.1 ohm. So this is the difference between series and parallel combination. Now we have seen how to arrive at the final or the equivalent resistance for series and equivalent resistance for parallel separately. Now what happens if we are given a combination of series and parallel in one particular circuit? How are we going to solve it? So that we will just look at it right now. So in this circuit, let us take this as my R1, this as R2, and this as R3. So we have current that is coming. It splits into, let's say, I1 and I2, and again we get back I, because if I is equal to I1 plus I2 and it comes back here, we need to have current back in the circuit. Now when we look at it, what do we have? R2 is parallel to R3, and this combination is in series with R1. So that means first you have to solve the parallel combination. Always remember, it's an important thing. First solve the parallel combination. So once you solve the parallel combination, we will get the equivalent resistance of R2 and R3, which is going to be in series with R1. So what we will do is we will draw an equivalent circuit diagram also. Till now, we have seen them separately, so we have not done any equivalent circuit. But here we will go ahead and draw an equivalent circuit and see how it happens once we reduce or once we find the equivalent width for the parallel combination. So resistance in parallel, if I take, I have got R2 parallel to R3. So resistance in parallel, we always take it as 1 by, always remember that, will be equal to 1 by R2 here plus 1 by R3. So we can take the LCM and solve. We will get it as R2 plus R3 by R2 R3, or RP will be equal to R2 R3 by R2 plus R3. This is in terms of ohms. We get it as 1 by, we have made sure that it is in RP. So how will the equivalent resistance now look? That is something that we'll have to draw. So from this combination that we had, we are going to have this particular combination. So this was R1 as it is. This is current I that is passing. Now this is our RP. So I have current that is coming. That means what have I done? I have written RP as R2 R3 by R2 plus R3. This is this combination here. So what has happened? This has reduced to a series circuit now. Now we cannot directly add series to a parallel combination. We need to have series and series. That means R1, R2 or R1, RP and so on. Everything to be in series to add them up. So first we go ahead and solve the parallel combination, and then only we look at the series combination. So now let us look at the next part of solving. So R series is going to be nothing but R1 plus R parallel, or this I can write it as R1 plus R2 R3 by R2 plus R3. Now this is going to be in terms of ohms itself. So the total resistance in series. So let's go ahead and draw an equivalent circuit for this and see how it is. So for this, the equivalent circuit will only look something like this. So you can see that from a complex circuit which had series and parallel combination, we reduced it to a simple circuit which had series combination, and finally we further reduced it to a combination like this. So we don't have two resistances anymore. So what is RS here? RS would be nothing but R1 plus R2 R3 by R2 plus R3. So we've got one simple circuit at the end of this simplification. Now for this final simplified circuit, let us have a look at what is the current that is passing by. So here if I see, we know that V is equal to IR. So what we will do, current is equal to V by R. In this case it is series, because that was our final or the equivalent value that we got, which is nothing but V by R1 plus R2 R3 by R2 plus R3. So let us just simplify this. So I'll get I is equal to V times R2 plus R3 divided by R1 R2 plus R1 R3 plus R2 R3. So we can have this as the value of current for combinations. So quickly we will have a look at all the formulas that we have for this part. Now we started off with the idea about charges that are moving. We went ahead and found out current. We'll take Ohm's law first. We had V equals IR. Then we went ahead and found out current density. I by A is equal to J, and V is equal to E times E vector. So we had current density as 1 by rho times E, that is 1 by resistivity. We took it as conductivity times E vector. We found the electric field is nothing but resistivity times the current density. Then we went ahead and calculated the drift velocity, that is current that is generated. I equals NE AVD, and the drift velocity was minus EM by tau by M. So minus EE tau by M. We again went ahead and found out what is the current density. So current density, since I have A here, I by A was NE VD, and on substituting the value of VD, the current density now becomes NE square E by M times tau. Here I have taken the modulus of VD. That means even though this is a vector that I have taken, I am taking only the magnitude, positive sign, and not the negative value. Next, we went ahead and calculated resistance in series to be nothing but R1 plus R2 plus R3 plus etc. plus Rn, which we can now write it as I is equal to 1 to N sigma Rn for N similar resistances. We have Rs is equal to N times R. We found out resistance in parallel, equivalent resistance as 1 by R1 plus 1 by R2 plus 1 by R3 plus etc. plus 1 by Rn, which we can write it. Now here again you have to be very careful, it has to be 1 by Rp. So Rp that is there, or 1 by Rp is equal to sigma 1 by Rn I equals 1 to N. This has to be done very carefully, otherwise what happens, we can tend to make mistakes. So for again N similar resistances, we find that now I can do Rp is equal to Rn by N. Because it is similar, I have just taken the reciprocal. After this, since it is parallel cases, we took the two different currents, I1 and I2 in the branches. We calculated that. We found it to be I2 as I, so I1 as I R2 by R1 plus R2, and I2 as I R1 by R1 plus R2. Then we saw the difference between the series and parallel combination. We also went ahead and solved uh, an expression or a circuit when we have both series and parallel. How do we draw equivalent circuits and come back to the simplest form of the given circuit? So for a series parallel combo, if we can call it like this, we found the final resistance to be R1 plus R2 R3 by R2 plus R3, and we went ahead and calculated what is the current, which is nothing but V times R2 plus R3 divided by R1 R2 plus R1 R3 plus R2 R3.